So now that we've had a brief introduction to the parallelism we've already seen in this course, let's talk about multi-core processors, why we have them, and what they are. So why did we care about parallelism? Well, we cared about it because we wanted to make our programs faster. And let's look at the different ways we can make them faster. So we can increase the clock speed. So this means we do more instructions per second. If we run at 2 gigahertz instead of 1 gigahertz, we can potentially do twice as many instructions per second and run twice as fast. We can do the instructions more efficiently, that is, spend fewer clock cycles per instruction. So this is the difference between the serial multiplier, where we needed 32 cycles to do a 32-bit multiplier, and the parallel multiplier, which only needed 1 cycle to do the multiplication. We can also do more instructions at the same time. So this gives us more instructions per second. And we saw this in the pipeline where we do 5 instructions at the same time. So if we look at these 3 ways of making processors run faster, we can see the first one is about building better transistors. The second one is about building better circuits. And the third one is about building more circuits. And that's what we're going to focus on in this lecture. How do we get parallelism by building more circuits, and how can we get performance from that? So why shouldn't we just increase the clock speed? That seems like the easiest way to make things run faster. So here's some data we saw at the beginning of the course. It gives us the year versus a scale, and the scale is logarithmic, and it shows us a bunch of information. Here's the relative performance. And we see as performance was increasing nice and exponentially, remember this is a log scale, up until about 2004, and then things got much slower. We can compare this to the clock speed, and you see what happened here is the clock speed kept increasing right until 2004, and then it stayed pretty much flat. Here's the power. Same thing with power, kept increasing until 2004 and then stayed pretty much flat. And this is sort of the driver for everything here. We hit what is known as the power wall. When we got to about 250 or 300 watts, we realized it was too expensive to cool the chips, and we just couldn't make them any hotter. So because we ran into this limit of power here, that forced us to limit our clock frequency and resulted in limited performance. So why did we hit the power wall? Well, let's take a look at the power for a transistor. So the transistor power is approximately C/V squared F, where C is the capacitance of the transistor, and this gets smaller as the transistors get smaller. So each time we come out with new smaller transistors, their area is smaller, so their capacitance is smaller. V is the voltage for a 1. So if it's 1.3 volts, V would be 1.3, or in the past we had 5 volt transistors, V would be 5. And this used to get smaller as transistors get smaller. Today it doesn't get smaller very much, and that's the real problem. And F is the frequency, so that's how fast we run our chip. So what you see here is we have a linear dependence on capacitance. If we double the capacitance, our power will double. We have a quadratic dependence on voltage. If we double our voltage, our power will quadruple. And we have a linear dependence on frequency. And the key thing to remember is that voltage used to get smaller as transistors got smaller and doesn't anymore. So how can we adjust the power? Well, the capacitance doesn't actually help us. And the reason for that is transistors get smaller, so the capacitance per transistor goes down, but then we put more transistors on a chip. So as long as the size of the chip stays the same, the capacitance stays the same. V is our most effective way to reduce power. If we reduce voltage, we'll reduce power by the square. But voltage isn't going down anymore, and this is the real problem. If the voltage gets too low, the transistors get slower. And this is just a property of silicon. There's a voltage below which the transistors just don't work very quickly, and we've already approached that voltage. The other problem is as we increase voltage, we get closer to something called the threshold voltage. The threshold voltage is the point where the transistor turns on and off. And the closer to this you get, the more leakage you have. And leakage is where electricity just runs through the transistor, regardless of whether it's on or off. And the more leakage you get, that's just wasted energy, which caused wasted power. So we can't keep bringing voltage down. And if we can't reduce voltage, that means we can't increase frequency because we'd increase our power. So we can't increase the clock speed for performance. Here we have our clock speed, and you can see it's leveled off here. And that's because if we increase our clock speed, we're going to directly increase our power. And we can't decrease the voltage to compensate. So here's our power, and you can see the power is pretty much leveled off when we leveled off our clock speed. This was the power wall we ran into. And so what did people do? Well, they said we can't increase the clock speed, but we still need a way to say our chips are faster, so somebody will buy them, so we'll put more cores on them. And this is multi-core. So we've increased from having 1 core per chip up to about 2004 to now we have 8, 16, 4, many cores on each chip. And the reason we ran into this power wall, as I've said before, and this is a key thing to remember, is we can't reduce our voltage. And if we can't reduce voltage, the power goes up if we increase frequency. So that limits how much we can increase the frequency. All right, so what is multi-core? Well, it's to a large extent selling you a new chip you can't use. So Intel can't make the clock speed faster because it will use too much power, and that's because we can't reduce voltage anymore. So we need to find something to do with all those transistors that makes you want to buy a new chip. And so what do? Well, they go to multi-core. They say, I'll give you 2 cores, so it'll be twice as fast, so you should buy that, or maybe 4 cores, so it'll be 4 times as fast, and you should buy that. So question, is a 4-core machine faster for most programs? Well, the answer here is it depends on the program. Programs that can divide their work up evenly into 4 chunks can run 4 times faster with 4 cores. But most programs can't do this. So Firefox doesn't have any way to divide a web page up into 4 even chunks. Word doesn't have any way to divide up spell checking into 4 even chunks, so they don't benefit from more cores. So now we're in the era of multi-core. Here's an example of an AMD chip, and this chip has 6 cores per chip, and then they put 2 chips together, you can see the border here, into one package and call it a 12-core chip. Here's a 6-core chip from Intel. Looks very similar. You've got your 6 cores and a whole bunch of cache attached to it. Here's an 8-core chip from China. So this is the Chinese government has gotten together and made their own processor, and each one of these cores is basically a MIPS core with some special instructions so they can run x86 code efficiently. Here's an Oracle Spark processor. It has 16 cores, and again you see here are all the cores, and then here's all the cache. And if you notice, the Spark processor has much less cache per core than either the Intel or the AMD processors. It's because they're optimizing for different things. Here's IBM's 18-core Blue Gene Q. You can see all of the cores are here around the edges, and you've got the huge cache sitting in the middle. And this chip is designed for large-scale scientific computing. And here's Intel's new 62-core Xeon Phi. This is also designed for scientific computing. And here you don't see a large cache because each of these cores has a cache inside of it. And together all of those caches add up to one big cache. So clearly everything's moving to multi-core. And the reason for that is that we need a way to advertise more performance even though we can't increase the frequency because we can't reduce the voltage and we're power limited. All right, so is multi-core faster? So here we are increasing our number of cores, and here's our performance change, and well, it's not so much faster. Look how much we've increased our core count, but our performance hasn't gone up that much. So what's going on? Well, the reason we have multi-core, as I said before, and it's important to remember this, is we can't reduce the voltage. So power goes up if we try to increase frequency. Intel wants to figure out a way to sell you a new chip, so they use the transistors to build more cores and try and convince you it'll run faster. But the problem is it doesn't help for most programs. We're going to see that in a little bit, how it's hard to get programs to be parallel. So what is the most effective way to reduce power in a transistor? Well, it's to use lower voltage. Remember, power equals CV squared F. So if we cut the voltage in half, we'll cut the power by 1/4. But as I've emphasized several times now, we can't reduce the voltage that much anymore because we're limited by what silicon can do. If we reduce the voltage any further, the transistors get slow, and we get close to the threshold voltage, and they start to leak current. And when we leak current, that's energy that's not doing useful work, so it increases the power without increasing performance. Why can't we increase the frequency anymore? Well, the reason is the answer is all of the above here. So we're power limited. If we increase F, we're going to get a linear power increase. And we used to get around this by decreasing voltage, but we can't reduce voltage anymore. And while capacitance does go down for every transistor, we put more transistors on a chip, so the total capacitance for the chip stays the same.